Take the space between your fingers right now. You think it's empty, but 2025's quantum experiments reveal it's actually buzzing with particles that continuously appear and vanish. This isn't science fiction. Because of quantum uncertainty, perfect emptiness cannot exist. Every cubic centimeter of empty space contains measurable zero-point energy, the baseline quantum activity that persists even at absolute zero temperature. Recent breakthroughs at Oxford University have achieved real-time simulations of how laser beams alter the quantum vacuum itself, proving these effects are not just theoretical. The question that's haunting physicists: if nothingness is impossible, what does this mean for reality itself? This mystery has puzzled humanity for centuries, and the answer changes everything we thought we knew about existence. The ancient mystery that stumped humanity. For 24 centuries, humans have wrestled with a question that seems simple but refuses to yield an answer. What exists in the gap between two objects when you strip away everything visible? Look at the space between your thumb and index finger. Remove the air, the dust particles, the invisible moisture, every single atom. What remains in that space? The question has tormented philosophers, puzzled scientists, and shaped entire civilizations' understanding of reality. Aristotle, writing in ancient Greece around 350 BCE, confronted this mystery and reached a conclusion that would dominate human thinking for over a millennium. The idea of true emptiness disturbed him deeply. It created logical paradoxes and seemed to violate the natural order. After careful consideration, he declared that nature abhors a vacuum. These four words became doctrine, carved into the foundation of human knowledge, and defended with religious fervor by scholars across Europe and the Middle East. The evidence seemed to support Aristotle's claim everywhere people looked. When you suck air from a drinking straw, more air immediately rushes in to replace what you removed. Block the bottom and suck harder, and the straw walls collapse inward, as if the universe itself is fighting your attempt to create emptiness. Nature appeared to mobilize every force at its disposal to prevent the creation of nothingness. Medieval scholars built elaborate theories around this principle. They imagined that invisible substances must fill every corner of space, that matter would rather stretch and compress than allow true emptiness to exist. The concept became so fundamental that questioning it bordered on heresy. Universities taught Aristotle's physics as absolute truth, and generations of thinkers accepted that vacuum was not just difficult to create, but impossible by the very laws of nature. Yet in 2025, our most advanced quantum laboratories have shattered this ancient certainty. Scientists now create vacuum chambers that remove 99.999999999% of all matter, approaching the theoretical limit of emptiness. These chambers, cooled to temperatures colder than deep space and isolated from every possible disturbance, should contain nothing by any classical definition. Instead, they reveal a shocking truth that would have terrified Aristotle: apparent emptiness teems with activity. Modern quantum field theory predicts that what we call empty space hosts constant fluctuations at the smallest scales. Particles materialize from nothingness, exist for impossibly brief moments, then vanish back into the void. The vacuum isn't empty. It's the universe's most dynamic environment. This revelation matters more in 2025 than ever before because our technology has reached the point where we can directly observe and manipulate these quantum effects. Particle accelerators now routinely create matter from apparent emptiness, proving that the void contains hidden creative potential. Quantum computers harness vacuum fluctuations to perform calculations impossible with classical systems. Our most sensitive gravitational wave detectors must account for quantum vacuum noise to achieve their unprecedented precision. The implications extend far beyond laboratory curiosities. Dark energy, the mysterious force accelerating the universe's expansion, may originate from the quantum properties of empty space itself. The cosmic microwave background radiation, Light from the universe's infancy carries signatures of quantum vacuum fluctuations magnified to cosmic scales. Every galaxy, star, and planet may owe its existence to quantum effects in primordial nothingness. Understanding vacuum physics has become crucial for predicting the universe's ultimate fate. If empty space contains energy that can drive cosmic expansion, will this expansion continue forever? Or might vacuum instability trigger a catastrophic collapse? Some theories suggest our current vacuum state might be metastable, like a ball balanced on a hilltop, capable of rolling into a lower energy state and rewriting the laws of physics throughout the universe. The journey from Aristotle's philosophy to quantum field theory represents one of humanity's greatest intellectual achievements. Ancient Greeks could only observe nature with their senses and reason with pure logic. Today's physicists use instruments that detect phenomena occurring in billionths of a second across distances smaller than atomic nuclei. They probe energy scales where spacetime itself becomes uncertain, where the boundary between existence and non-existence blurs beyond recognition. This transformation in understanding required abandoning deeply held intuitions about reality. Aristotle's conviction that nature abhors a vacuum felt obviously true because it matched everyday experience. Yet quantum mechanics reveals that this intuition, like many others, fails at the fundamental level where reality operates according to principles that seem to violate common sense. The experimental proof continues mounting in 2025. Researchers at quantum optics laboratories measure vacuum fluctuations directly using superconducting circuits and laser interferometry. They observe how these fluctuations affect atomic energy levels, creating measurable shifts in spectral lines. Space-based experiments study vacuum properties in environments more isolated than any earthbound laboratory can achieve. Each measurement confirms that the classical concept of empty space as passive nothingness bears no resemblance to physical reality. What emerges is a picture of existence where the void plays the leading role rather than serving as a passive backdrop. Vacuum fluctuations may explain why matter exists at all instead of having been completely annihilated by antimatter in the early universe. They might drive the formation of cosmic structure, influence the behavior of fundamental particles, and determine the stability of physical laws themselves. The ancient mystery that stumped humanity for millennia turns out to have an answer more strange and wonderful than any philosopher imagined. Nothingness isn't the absence of everything, it's the presence of infinite potential. Yet this understanding only emerged after centuries of Aristotelian doctrine were finally challenged by a simple but revolutionary experiment that would change everything. The first crack in reality's foundation. The breakthrough came from an unlikely source in 1640s Italy. Evangelista Torricelli, a mathematician working for Galileo, faced a practical problem that would accidentally crack open humanity's oldest mystery. Italian well diggers had discovered something disturbing. Their pumps could lift water only about 34 feet, no matter how powerful they made them. Beyond that height, the water simply refused to rise, as if hitting an invisible ceiling. The phenomenon baffled engineers across Europe, who had been building increasingly ambitious fountains and water systems. Torricelli suspected the answer lay not in the limitations of pumps, but in the weight of air itself. He devised an experiment so simple it could be performed in any workshop, yet so revolutionary it would shatter over a millennium of accepted wisdom about nature. Instead of water, he chose mercury, which weighs 14 times more than water. He filled a 4-foot glass tube completely with mercury, sealed one end with his finger, then flipped it upside down into a bowl of mercury. When he removed his finger, something extraordinary happened. The mercury dropped to exactly 760 millimeters and stopped. Above it, in the top of the tube, was a space containing no mercury, no air, no visible substance whatsoever. Torricelli had created the first controlled vacuum in human history. The empty space above the mercury column became known as the Torricellian vacuum, and it defied everything Aristotle had taught about nature's supposed hatred of emptiness. Here was nothingness, created not through some cosmic accident, but through simple mechanical means that anyone could reproduce. The implications hit the scientific community like an earthquake. If nature truly abhorred a vacuum, why didn't the mercury rise to fill the entire tube? Why did it stop at precisely 760 millimeters, leaving that mysterious empty space behind? Torricelli realized the answer revealed something profound about the world we inhabit. The mercury column was being held up by the weight of the entire atmosphere pressing down on the mercury in the bowl below. We live, he concluded, at the bottom of an ocean of air. This revelation transformed humanity's understanding of Earth's place in the cosmos. The atmosphere wasn't some ethereal substance surrounding the planet. It was a physical ocean with measurable weight and pressure. The air pressing down on every square inch of Earth's surface exerted a force of nearly 15 pounds. Torricelli's tube had become the first instrument capable of measuring this invisible ocean, and the empty space above the mercury provided the first window into what lay beyond. But what exactly existed in that vacant space above the mercury? The tube contained no air, because air had been displaced by the mercury before the tube was inverted. No dust or moisture could survive the mercury's dense environment. By every measure available to 17th century science, the space was truly empty. Yet questions nagged at curious minds. If this space contained absolutely nothing, why didn't more mercury rise to fill it? What prevented nature from collapsing this void? The experiment sparked a frenzy of investigation across Europe. In France, Blaise Pascal expanded on Torricelli's work with even more dramatic demonstrations. Pascal carried a mercury barometer up the Puy de Dôme mountain and observed something remarkable. The mercury level dropped significantly between the base and summit. This measurement proved that atmospheric pressure decreases with altitude, confirming that Earth's ocean of air had a definite top. Pascal's mountain experiment revealed the terrifying truth about space itself. If atmospheric pressure decreased with altitude, then at some height, it must disappear entirely. Beyond Earth's atmosphere lay a vacuum so vast it dwarfed any laboratory creation. The space between planets, between stars, between galaxies was empty in ways that challenged human comprehension. The universe consisted mostly of nothingness, with tiny islands of matter scattered through an infinite sea of vacuum. These revelations connected to 2025's most sophisticated vacuum technology in ways the early experimenters could never have imagined. Modern ultra-high vacuum chambers achieve emptiness levels 1 trillion times more complete than Torricelli's simple tube. Where his mercury barometer removed ordinary air, today's systems eliminate individual atoms using techniques that would seem like magic to 17th century eyes. Ion pumps, cryogenic cooling, and magnetic fields work together to approach the theoretical limits of emptiness. Yet even 2025's most advanced vacuum chambers cannot achieve what Torricelli's contemporaries thought his tube contained: true nothingness. Quantum mechanics reveals that perfect vacuum violates fundamental physical principles. The uncertainty principle prevents any region of space from containing exactly zero energy for any measurable time. What 17th century scientists celebrated as empty space actually seethes with quantum activity, invisible to classical physics. The progression from Torricelli's mercury to modern quantum vacuum research illustrates humanity's expanding ability to probe reality's deepest levels. His glass tube revealed that emptiness could be created and measured. Today's instruments detect the quantum fluctuations that make true emptiness impossible. Both discoveries required abandoning intuitive assumptions about how the world works. Both revealed that reality operates according to principles that seem to violate common sense. Torricelli's simple experiment opened a door that science has been walking through for nearly 4 centuries. Each generation discovers new layers of complexity in what initially appeared to be simple emptiness. But as the 19th century dawned, scientists would face an even deeper puzzle about the nature of empty space, one that would challenge everything they thought they understood about how the universe worked. The invisible ocean that wasn't there. By the 1800s, scientists faced a troubling contradiction that threatened the foundation of physics. Light behaved like a wave in every experiment they performed. When light passed through narrow slits, it created interference patterns identical to water waves colliding with each other. When light reflected off surfaces, it followed the same mathematical rules that governed waves bouncing off barriers. The wave nature of light seemed beyond dispute, yet this created an impossible puzzle. James Clerk Maxwell's groundbreaking equations had unified electricity and magnetism, revealing that light was an electromagnetic wave. But this triumph created a deeper mystery. Every wave that scientists had ever studied required a medium to carry it. Sound waves traveled through air, water waves moved through liquid, vibrations in solid materials transmitted through the material itself. Without these media, the waves simply couldn't exist. Maxwell's equations described electromagnetic waves perfectly, but they said nothing about what medium supported these waves through space. But light presented a maddening exception. Sunlight reached Earth after traveling through the vacuum of space for 8 minutes. Starlight crossed vast empty distances to reach telescopes on Earth. If light was truly a wave, what medium carried it through these empty regions? The scientific community reached a consensus that seemed logical and necessary. Space couldn't actually be empty. An invisible substance must fill every corner of the universe, providing the medium that electromagnetic waves needed to propagate. They called this mysterious substance the luminiferous ether. The name itself revealed their confidence in its existence. Luminiferous meant light-bearing, and ether referred to the classical element that ancient Greeks believed filled the heavens. This wasn't just a theoretical speculation. It was presented as a scientific fact. Physics textbooks described the ether's properties with the same certainty they used for describing gravity or magnetism. The ether theory required this substance to possess extraordinary characteristics that pushed the boundaries of believability. It had to fill absolutely all space, from the gaps between atoms to the vast distances between galaxies. Yet it had to be completely transparent, allowing light to pass through without any absorption or scattering. It needed to be massless, so it wouldn't affect the motion of planets and stars. It had to be frictionless, because celestial bodies showed no signs of slowing down as they moved through it. Most puzzling of all, the ether had to be completely undetectable by any mechanical means. Scientists couldn't feel it, weigh it, or see its effects on ordinary matter. It had to be rigid enough to support the rapid vibrations of light waves, yet flexible enough to allow solid objects to pass through it without resistance. These contradictory requirements should have raised red flags, but the alternative seemed worse. Without the ether, electromagnetic waves had no explanation for their existence. The pressure to detect and measure this cosmic fluid intensified throughout the 19th century. Scientific reputation and entire research careers hinged on solving the ether puzzle. Universities across Europe and America funded elaborate experiments designed to reveal the ether's properties. The most brilliant physicists of the era devoted their lives to this quest, convinced that understanding the ether would unlock the deepest secrets of the universe. The challenge seemed straightforward in principle, but proved impossible in practice. If Earth moved through the ether as it orbited the Sun, there should be an ether wind detectable from Earth's surface. This wind would affect the speed of light traveling in different directions, just as a river current affects the speed of boats traveling upstream versus downstream. Measuring these tiny speed differences would reveal the ether's properties and confirm its existence. But the ether defied every attempt at detection. Instruments capable of measuring incredibly small changes in light speed showed no variation in any direction. Experiments designed to detect ether currents found nothing. Sophisticated optical devices that should have revealed the ether's influence on light propagation produced null results. The harder scientists looked, the more elusive the ether became. The search for ether drove the development of precision measurement techniques that pushed 19th century technology to its absolute limits. Scientists built interferometers capable of detecting length changes smaller than a fraction of a light wavelength. They constructed rotating platforms to eliminate the effects of Earth's rotation. They performed experiments at different times of year when Earth's orbital motion changed direction. Every refinement in technique should have brought them closer to detecting the ether, but instead it confirmed its absence. Today's understanding of electromagnetic fields eliminates the need for any medium in space. Maxwell's equations, refined and confirmed by countless experiments, show that light is a self-sustaining oscillation of electric and magnetic fields. These fields don't require a substrate to exist. They are fundamental properties of space itself. Light waves propagate through vacuum, not because vacuum contains a hidden medium, but because electromagnetic fields can exist and oscillate in empty space. The mounting evidence against the ether created an increasingly desperate situation in physics. Every experiment designed to prove the ether's existence instead demonstrated its absence. Every refinement in measurement technique made the null results more definitive. The scientific community faced a choice between abandoning a theory that seemed logically necessary or accepting experimental results that defied their understanding of how waves should behave. This crisis demanded a definitive resolution. The most sophisticated measurement techniques of the era would need to be brought to bear on the problem. If the ether existed, even the most subtle effects of Earth's motion through it should be detectable with sufficient precision. The stage was set for an experiment that would either vindicate decades of ether theory or shatter the foundations of 19th century physics. The experiment that broke physics. Albert Michelson had already established himself as America's premier expert in precision optics when he partnered with Edward Morley in 1887 to conduct what they believed would be the definitive experiment of the century. Their goal seemed straightforward: measure Earth's motion through the luminiferous ether by detecting tiny variations in light speed. The scientific community waited with anticipation for results that would finally confirm the ether's existence and reveal its fundamental properties. Michelson and Morley constructed an interferometer of unprecedented sensitivity, capable of detecting speed differences as small as 1 part in 100 million. The device split a single beam of light into 2 perpendicular paths using a half-silvered mirror. One beam traveled east-west, the other north-south, before both reflected off mirrors and recombined. If Earth moved through the ether, the beam traveling parallel to Earth's motion should take slightly longer to complete its journey than the beam traveling perpendicular to it. The apparatus sat on a massive stone slab floating in a pool of mercury to eliminate vibrations that might obscure the delicate measurements. The entire setup could be rotated smoothly, allowing the experimenters to change the orientation of the light paths relative to Earth's motion. Theory predicted that rotating the apparatus would create a characteristic pattern of changes in the interference fringes, revealing both the direction and magnitude of Earth's ether wind. The mathematical prediction was clear and unavoidable. Earth orbits the Sun at roughly 30 kilometers per second, creating an ether wind that should affect light propagation. When light traveled against this wind, it should slow down, just like a swimmer struggling upstream. When light traveled with the wind, it should speed up. The interferometer would detect these speed differences by observing shifts in the interference pattern created when the 2 beams recombined. Michelson and Morley spent months calibrating their instrument and eliminating potential sources of error. They performed the experiment at different times of day to account for Earth's rotation. They repeated measurements across different seasons when Earth's orbital velocity pointed in different directions relative to the solar system. Every precaution was taken to ensure that when the ether wind finally revealed itself, no one could question the validity of the detection. The results shattered every expectation. No matter how they oriented the apparatus, no matter when they performed the measurements, the speed of light remained absolutely constant. The interference pattern showed no shifts, no variations, no hint of the ether wind that should have been easily detectable. Light traveled at exactly the same speed in all directions, completely independent of Earth's motion through space. The null result was so unexpected that Michelson and Morley initially assumed their experiment had failed. They checked and rechecked their apparatus, searching for systematic errors that might explain why they couldn't detect what should have been an obvious effect. The interferometer worked perfectly, producing clear interference patterns that responded predictably to deliberate disturbances. Yet it showed absolutely no evidence of the ether that every physicist knew must exist. The implications were staggering and immediate. If no ether wind existed, then the fundamental assumptions about light propagation were completely wrong. The scientific community faced a choice between clinging to increasingly desperate explanations or accepting that their understanding of electromagnetic waves needed complete revision. Albert Einstein provided the revolutionary solution in 1905 with his special theory of relativity. Einstein proposed that light needs no medium to propagate, and that the speed of light in vacuum represents a fundamental constant of nature. Space and time themselves adjust to ensure that all observers measure the same light speed, regardless of their motion. The ether simply doesn't exist because electromagnetic waves, as described by Maxwell's equations, are self-sustaining oscillations that require no material support. Einstein's insight transformed the null result from a failure into a triumph. The Michelson-Morley experiment hadn't failed to detect the ether. It had successfully demonstrated that empty space could indeed be truly empty. Light propagates through vacuum not because vacuum contains a hidden substance, but because electromagnetic fields can exist and oscillate without any underlying medium. Modern laser interferometry has elevated the precision of these measurements to levels that would astound Michelson and Morley. Today's gravitational wave detectors use laser interferometers billions of times more sensitive than the 1887 apparatus. The Laser Interferometer Gravitational Wave Observatory can detect length changes smaller than 1,100,000, the width of a proton. Yet these instruments continue to confirm that light speed remains absolutely constant in all directions. The technological sophistication of 2025's experiment provides overwhelming confirmation of Einstein's insights. Atomic clocks synchronized by laser pulses maintain accuracy to within nanoseconds across continental distances. Global positioning satellites rely on the constancy of light speed to provide navigation accuracy within meters. Every measurement continues to support the conclusion that light propagates through genuine vacuum without requiring any underlying medium. The Michelson-Morley experiment marked the end of classical physics and the beginning of the modern era. Their null result opened the door to relativity theory, quantum mechanics, and our current understanding of spacetime as a dynamic entity that can bend, stretch, and vibrate. What seemed like experimental failure became the foundation for revolutionary insights about the nature of reality itself. The profound realization emerged that scientists had finally encountered true nothingness in the vacuum through which light travels. For the first time in human history, absolute emptiness seemed not only possible, but necessary for understanding how the universe actually works. Yet this scientific breakthrough would soon trigger an unexpected consequence that nobody anticipated. When nothing became big business, industries quickly recognized that creating empty space could generate enormous profits. Thomas Edison's incandescent light bulb in 1879 required removing air from inside the glass bulb to prevent the carbon filament from oxidizing and burning out within seconds. Without vacuum technology, electric lighting would have remained impossible, and cities worldwide would have continued relying on gas lamps and candles for illumination. The economic potential became clear immediately. Every household, office, and street corner represented a potential customer for vacuum-sealed light bulbs. Edison's company needed to produce millions of bulbs annually, each requiring its own carefully evacuated glass envelope. This demand drove rapid innovations in vacuum pump design and mass production techniques. Glass blowers learned to seal bulbs while maintaining near-perfect vacuum inside. Pump manufacturers competed to build faster, more reliable equipment that could evacuate thousands of bulbs per day. The Fleming valve, patented in 1904, demonstrated how vacuum technology could expand beyond simple lighting. This device used a vacuum-sealed glass envelope containing metal electrodes to amplify weak electrical signals, making radio broadcasting possible and launching the communications revolution. Radio manufacturers discovered they were essentially selling controlled nothingness wrapped in glass. Each vacuum tube contained space more empty than anything found naturally on Earth. Yet this emptiness had measurable economic value. The mass production of vacuum tube transformed them from expensive laboratory curiosities into consumer products affordable for ordinary families. Assembly line techniques reduced the cost of evacuating glass envelopes from dollars per unit to pennies per unit. Automatic glassworking machines could produce thousands of identical tubes daily, each sealed under precisely controlled vacuum conditions. This industrial revolution made radios, televisions, and other electronic devices accessible to middle-class households throughout America and Europe. The economic boom extended beyond consumer electronics into scientific instrumentation. Researchers needed vacuum chambers for studying atomic particles, measuring the properties of materials, and conducting experiments impossible in the presence of air. Universities and government laboratories purchased increasingly sophisticated vacuum systems, creating a specialized market for high-performance pumps, gauges, and sealing materials. This commercial vacuum industry inadvertently enabled the scientific discoveries that would revolutionize physics. Wilhelm Röntgen discovered X-rays in 1895, while experimenting with a vacuum tube designed for studying electrical discharges. The empty space inside his tube allowed high-energy electrons to travel unimpeded from cathode to anode, generating mysterious rays that could penetrate solid materials. Without commercial vacuum technology, this breakthrough might have been delayed by decades. J.J. Thomson's discovery of the electron in 1897 also depended on commercially produced vacuum tubes. Thomson used cathode ray tubes originally developed for early television experiments to study the behavior of electrical discharges in near-perfect vacuum. By carefully controlling the emptiness inside his apparatus, he could observe individual subatomic particles for the first time in human history. The electron, the fundamental building block of all matter, was discovered inside a volume of commercialized nothingness. Ernest Rutherford's experiments revealing atomic structure required vacuum chambers that allowed alpha particles to travel in straight lines without colliding with air molecules. His famous gold foil experiment, which discovered the atomic nucleus, was performed inside an evacuated chamber that removed every trace of interfering matter. The architecture of atoms was mapped using controlled volumes of empty space produced by industrial vacuum technology. The semiconductor industry of 2025 demonstrates the continued economic importance of vacuum technology. Modern microchip fabrication requires ultra-high vacuum environments cleaner than outer space. Silicon wafers are processed in chambers where the vacuum quality approaches theoretical perfection, with fewer than 1 billion molecules per cubic centimeter remaining. These conditions cost millions of dollars to create and maintain, yet they enable the production of computer processors worth hundreds of billions of dollars annually. Plasma deposition, ion implantation, and molecular beam epitaxy all depend on vacuum environments so pure that a single contaminating molecule can ruin an entire batch of microchips. The global semiconductor industry invests tens of billions of dollars annually in vacuum systems, pumps, and monitoring equipment. Companies compete to achieve ever higher levels of emptiness, pushing toward the theoretical limits of how empty space can become. The progression from Edison's light bulbs to modern semiconductor fabrication illustrates how commercializing nothingness drove both economic growth and scientific discovery. Each improvement in vacuum technology opened new possibilities for studying matter at smaller scales and higher energies. Better pumps enabled researchers to create emptier spaces, which revealed previously hidden phenomena operating at the boundaries between existence and non-existence. Particle accelerators, the tools that probe the deepest mysteries of matter and energy, represent the ultimate expression of commercialized vacuum technology. These machines create emptiness so complete that particles can travel for miles without encountering a single atom. The vacuum systems in modern accelerators cost hundreds of millions of dollars and require constant maintenance by teams of specialized technicians. The irony becomes clear when viewed from the perspective of 2025's quantum physics. The vacuum technology industry spent over a century perfecting methods for creating empty space, only to discover that perfect emptiness cannot exist. The commercial pursuit of selling nothing ultimately provided the tools that would reveal the most shocking truth about reality itself, that the very concept of nothingness might be fundamentally impossible. The quantum earthquake that shattered reality. In 1927, a young German physicist named Werner Heisenberg made a discovery that would demolish humanity's classical understanding of reality. Working at the forefront of the emerging quantum mechanics revolution, Heisenberg uncovered a fundamental principle that seemed to violate basic logic. He proved mathematically that nature itself prevents us from knowing certain things with perfect precision. You cannot simultaneously measure both the exact position and exact momentum of any particle, no matter how sophisticated your instruments become. This wasn't a limitation of measurement technology or human skill. Heisenberg demonstrated that the uncertainty was built into the fabric of reality itself. The more precisely you determine where a particle is located, the less precisely you can know how fast it's moving. The more accurately you measure its momentum, the fuzzier its position becomes. This trade-off isn't optional or avoidable. It represents a fundamental characteristic of how the universe operates at its smallest scales. The implications reached far beyond the behavior of individual particles. Heisenberg's uncertainty principle extended to other paired quantities, including energy and time. This created a loophole in the conservation of energy that seemed to violate one of physics' most sacred laws. For incredibly brief moments, the principle allowed energy to be borrowed from nothingness, provided it was returned quickly enough that the violation couldn't be detected. Consider what this means for supposedly empty space. Classical physics assumed that a perfect vacuum contained exactly zero energy at all times. But quantum mechanics revealed that measuring the energy content of any region of space with perfect precision was impossible. The uncertainty principle prevented nature from maintaining exactly zero energy in any volume for any measurable duration. This opened the door to phenomena that defied every intuition about how empty space should behave. The mathematics showed that vacuum could spontaneously produce virtual particles fluctuations in the vacuum, allowed by the uncertainty principle that manifest as short-lived electron-positron pairs. These virtual particles could pop into existence from pure nothingness, exist for impossibly brief moments, then annihilate each other and vanish back into the void. The smaller the region of space examined, the larger the energy fluctuations could become. The briefer the time interval considered, the more dramatic the violations of energy conservation that quantum mechanics permitted. This revelation transformed the concept of vacuum from passive emptiness into an active, dynamic medium seething with constant activity. Every cubic centimeter of apparently empty space hosted countless particle pairs appearing and disappearing. The vacuum became a bubbling foam of virtual particles, with matter and antimatter constantly materializing from nothingness and immediately destroying each other in flashes of pure energy. The first experimental proof came from Willis Lamb's precise measurements of hydrogen atom energy levels in 1947. Lamb discovered that electrons in hydrogen atoms exhibited tiny wobbles in their orbits that could only be explained by interactions with virtual particles in the surrounding vacuum. His measurements matched quantum electrodynamics predictions to 1 part in 100 million, providing direct evidence that vacuum fluctuations were real physical phenomena rather than mathematical abstractions. Modern quantum field experiments in 2025 have pushed these observations to unprecedented levels of precision and control. Researchers use superconducting circuits cooled to near absolute zero to observe individual quantum events in the vacuum. These devices can detect the appearance and disappearance of single virtual photons, measuring quantum fluctuations directly rather than inferring their existence from secondary effects. The experiments confirm that even the most sophisticated vacuum chambers contain measurable quantum activity. Advanced laser interferometry has revealed vacuum fluctuations through their effects on the propagation of light itself. Gravitational wave detectors must account for quantum noise in their vacuum chambers, where virtual particles create random fluctuations in the electromagnetic field. These fluctuations represent a fundamental limit to measurement precision, proving that perfect emptiness remains forever beyond experimental reach. The Max Planck Institute for the Structure and Dynamics of Matter has developed techniques where photons trapped inside optical cavities carry detailed information about quantum vacuum properties. By measuring the characteristics of photons leaking from these cavities, researchers can probe how empty space modifies the behavior of matter placed within it. These experiments reveal that vacuum isn't simply the absence of matter, but an active medium that participates in physical processes. Computational simulations now model vacuum fluctuations in real time, creating three-dimensional visualizations of how intense laser beams alter the quantum vacuum structure. These models recreate vacuum four-wave mixing, where three focused laser pulses can polarize virtual electron-positron pairs and generate a fourth laser beam from pure vacuum. The simulations show virtual particles responding to electromagnetic fields like a fluid medium, with complex internal dynamics. Researchers at the Institute for Quantum Computing have conducted the first experiments using quantum entanglement to extract energy from vacuum zero-point fluctuations. Their quantum energy teleportation protocol demonstrates that the vacuum's hidden energy can be accessed and manipulated using quantum mechanical techniques. These experiments transform theoretical speculation about vacuum energy into practical laboratory procedures. The accumulated evidence from decades of increasingly sophisticated experiments leads to an inescapable conclusion. The vacuum is not empty space waiting to be filled, but the most active environment in the universe. Virtual particles appear and vanish in numbers so vast they challenge human comprehension. Energy fluctuations occur on time scales so brief they make atomic processes seem leisurely. Yet understanding how these virtual particles could exist required a mathematical breakthrough that seemed impossible. The equations describing quantum mechanics and Einstein's relativity appeared fundamentally incompatible, creating contradictions that threatened the entire framework of modern physics. Resolving this crisis would require a mind capable of seeing mathematical patterns that had eluded every other physicist of the era. The genius who saw what others couldn't. Paul Dirac achieved something that had eluded the greatest minds in physics. Where others saw mathematical chaos, Dirac perceived elegant patterns hidden beneath the surface complexity. His extraordinary visual thinking allowed him to translate abstract mathematical relationships into mental pictures that revealed connections invisible to conventional approaches. Dirac possessed an almost supernatural ability to see mathematics as geometry in motion. While his colleagues struggled with pages of algebraic manipulations, Dirac could visualize the underlying symmetries and transformations that governed quantum systems. This unique cognitive gift enabled him to compress enormous complexity into simple, beautiful equations that captured fundamental truths about reality. His mathematical intuition operated more like artistic vision than conventional analytical reasoning. Maxwell's equations inherently supported special relativity by incorporating the constant speed of light, but merging quantum mechanics with electrodynamics required a new theoretical framework. Quantum electrodynamics, or QED, would unify these domains by describing how electrons and photons interact at the quantum level. Previous attempts had produced mathematical monsters filled with infinite terms and meaningless predictions. Dirac approached this problem with characteristic directness and mathematical elegance. He sought an equation that would describe electrons moving at any speed while preserving both quantum mechanical properties and relativistic constraints. The mathematics required him to work with four-component wave functions instead of the single-component functions used in ordinary quantum mechanics. This expansion seemed like a technical detail, but it contained revolutionary implications. The Dirac equation, when finally completed, appeared deceptively simple. 4 lines of mathematical symbols captured the behavior of electrons throughout the entire range from stationary to near light speed. The equation's solutions matched every experimental observation of electron behavior while maintaining perfect consistency with both quantum mechanics and special relativity. It represented one of the most successful theoretical achievements in the history of physics. But the equation contained something unexpected and deeply troubling. The mathematical solutions included terms that described particles with negative energy states. In classical physics, negative energy made no sense. An electron with negative energy would have less than zero energy, which seemed like a meaningless concept. Most physicists assumed these negative energy solutions were mathematical artifacts that should be discarded as unphysical. Dirac refused to dismiss the negative energy solutions. His visual intuition suggested that these mathematical ghosts might represent something real and important. He developed a radical interpretation that transformed apparent failure into revolutionary insight. According to Dirac's vision, the vacuum was not empty space, but a sea filled with electrons occupying all possible negative energy states. This infinite ocean of negative energy electrons remained invisible because it represented the baseline condition of empty space. The truly revolutionary prediction emerged from this interpretation. If one of these invisible negative energy electrons gained enough energy, it could jump to a positive energy state and become a normal, observable electron. But this process would leave behind a hole in the sea of negative energy electrons. This hole would behave like a particle with opposite properties to the electron, the same mass but opposite electric charge. Dirac had predicted the existence of antimatter. When Dirac published his antimatter prediction in 1930, most physicists considered it an interesting mathematical curiosity with no connection to physical reality. The idea that every particle had a mirror image partner with opposite properties seemed too strange to be true. The prediction implied that electrons had anti-electron partners, protons had antiproton counterparts, and every form of matter had a corresponding antimatter twin. The experimental confirmation came just 2 years later when Carl Anderson detected positrons in cosmic ray experiments. These anti-electrons behaved exactly as Dirac's equation predicted, possessing the same mass as electrons, but carrying positive electric charge instead of negative charge. The discovery vindicated Dirac's refusal to ignore the troubling mathematical terms that had seemed meaningless to everyone else. The implications extended far beyond the mere existence of antimatter particles. Dirac's work revealed the mechanism by which particles could appear from apparent emptiness and vanish again. When matter and antimatter particles meet, they annihilate each other completely, converting their mass into pure energy according to Einstein's equation. This process is perfectly reversible. Sufficient energy can create matter-antimatter pairs from vacuum. Modern research has pushed these insights into extreme regimes where nonlinear QED effects become observable. At extreme laser intensities, the quantum vacuum itself can be polarized and manipulated. Lili Zhang's 2025 simulations using the OSIRIS framework demonstrate how 3 focused laser pulses can generate a 4th beam through vacuum 4-wave mixing, where virtual electron-positron pairs respond to electromagnetic fields like a fluid medium with complex internal dynamics. The most profound insight from Dirac's work concerns the nature of empty space itself. His equation revealed that vacuum is not passive emptiness, but an active medium filled with virtual particle pairs constantly appearing and vanishing. Every point in space hosts a continuous dance of matter and antimatter creation and annihilation, with particles borrowing energy from the quantum vacuum and returning it before their existence can be detected. This revolutionary understanding transformed nothingness from a philosophical abstraction into a measurable physical phenomenon. The quantum vacuum became a dynamic entity with its own energy density and pressure, capable of influencing the behavior of matter and the expansion of the universe itself. Dirac's visual genius had uncovered the hidden activity that makes true emptiness impossible. Yet proving these theoretical predictions would require experimental techniques that seemed almost impossible to achieve. Catching ghosts in the machine. Willis Lamb changed everything in 1947 with an experiment so clever it earned him the Nobel Prize. Instead of trying to catch virtual particles in the act of existing, Lamb decided to measure their fingerprints left behind on ordinary matter. He focused on hydrogen atoms, the simplest atoms in the universe, which contain just one electron orbiting a single proton. According to existing theory, this electron should occupy energy levels that could be calculated with mathematical precision. But Lamb suspected that virtual particles from the quantum vacuum might interfere with these calculations. Lamb's experimental setup used radio waves to probe the energy levels of hydrogen atoms with unprecedented accuracy. He created hydrogen gas inside a vacuum chamber, then bombarded the atoms with precisely tuned radio frequencies. When the radio waves matched specific energy differences between electron orbits, the atoms would absorb the radiation and jump to higher energy states. By measuring which frequencies caused these transitions, Lamb could map the actual energy levels inside hydrogen atoms. The results revealed something extraordinary. The measured energy levels didn't match the theoretical predictions exactly. There was a tiny shift, smaller than 1 part in a million, but definitely present and measurable. This shift meant that virtual particles from the quantum vacuum were actually nudging electrons in their orbits, creating tiny wobbles that changed the energy levels by microscopic but detectable amounts. The ghost particles had left their signature on every hydrogen atom in the universe. The precision required for this measurement challenged the limits of 1940s technology. Lamb needed to detect energy differences equivalent to observing a grain of sand moving 1 millimeter while standing on the opposite side of Earth. The radio frequency measurements had to be accurate to within parts per billion to resolve the vacuum-induced shifts from other effects. Every stray magnetic field, temperature fluctuation, or vibration could mask the delicate signal that proved virtual particles existed. Modern quantum sensors have pushed these measurements to levels that would astound Lamb and his contemporaries. Atomic clocks now achieve precision, where quantum vacuum fluctuations represent a measurable source of uncertainty. These devices use laser-cooled atoms trapped in carefully controlled environments to measure time intervals, with accuracy approaching 1 part in a quintillion. At this level of precision, the constant activity of virtual particles creates detectable noise that limits the ultimate performance of the most accurate timepieces ever built. Superconducting circuits have opened entirely new windows into the quantum vacuum. These devices operate at temperatures colder than deep space, where thermal noise disappears and quantum effects dominate completely. Researchers can now watch individual photons appear and disappear from vacuum fluctuations, observing the birth and death of virtual particles in real time. The circuits act like amplifiers for quantum noise, making the normally invisible activity of the vacuum audible as a constant hiss of quantum static. Laser interferometry has revealed vacuum fluctuations through their effects on light propagation itself. The most sensitive gravitational wave detectors must account for quantum noise in their vacuum chambers, where virtual particles create random fluctuations in the electromagnetic field. These fluctuations represent the fundamental limit to measurement precision, proving that perfect stillness remains forever beyond experimental reach. Even laser beams traveling through the best vacuum chambers ever created encounter constant interference from virtual particle activity. Space-based quantum experiments launched in 2025 have extended these studies beyond Earth's atmosphere into the ultimate emptiness between planets. These satellites carry atomic interferometers and laser systems into environments more isolated than any Earthbound laboratory can achieve. Free from terrestrial vibrations, magnetic fields, and atmospheric interference, these experiments probe vacuum properties under conditions approaching theoretical perfection. The data reveals that even interplanetary space, empty beyond terrestrial imagination, seethes with quantum activity. The agreement between theoretical predictions and experimental measurements has reached unprecedented levels of accuracy. Quantum electrodynamics calculations of the Lamb shift match laboratory observations to better than 1 part in a trillion, making this the most precisely tested theory in the history of science. Every decimal place of agreement represents years of theoretical work and experimental refinement, building confidence that scientists truly understand the quantum mechanical basis of virtual particle effects. Advanced experiments now observe vacuum fluctuations directly rather than inferring their existence from secondary effects. Researchers use squeezed light states and quantum entanglement to probe the vacuum's quantum mechanical properties, with techniques impossible just decades ago. These experiments reveal that vacuum fluctuations have measurable statistical properties, energy distributions, and correlation patterns that can be studied like any other physical phenomenon. The cumulative evidence from 75 years of increasingly sophisticated experiments leads to an inescapable conclusion. The quantum vacuum is not empty space waiting to be filled, but the most active environment in the universe. Virtual particles appear and vanish in numbers beyond counting, creating constant fluctuations that affect every atom, every photon, and every measurement performed anywhere in the cosmos. Even the most perfect vacuum chambers, isolated from every possible disturbance and cooled to temperatures approaching absolute zero, contain measurable quantum activity that can never be eliminated. The ghosts have been caught, not through direct observation, but through the countless tiny effects they leave on everything around them. Virtual particles remain forever invisible, existing for time periods too brief for any detector to capture. Yet their influence permeates every corner of reality, from the energy levels of hydrogen atoms to the precision limits of atomic clocks. This discovery would soon reveal that the quantum vacuum's influence extends far beyond laboratory measurements, leaving its mark on the largest structures in the universe itself. The cosmic fingerprints of nothing. The cosmic microwave background radiation, discovered accidentally in 1965, carries within it the most extraordinary secret in the universe. Hidden in the tiny temperature variations of this ancient light lies proof that quantum vacuum fluctuations shaped everything we see around us. These minute differences in temperature across different regions of the sky measure just millionths of a degree. Yet they represent the fossilized imprints of quantum fluctuations that existed when the universe was smaller than a grape. During the universe's earliest moments, quantum mechanics ruled supreme. Space itself was so compressed that Heisenberg's uncertainty principle created fluctuations in energy density throughout the primordial quantum vacuum. These fluctuations followed the same statistical laws that govern virtual particles appearing and vanishing in modern laboratory chambers. But something remarkable happened to these microscopic quantum effects during a period cosmologists call inflation. Inflation theory describes how the universe underwent exponential expansion in its first fraction of a second. This violent stretching took quantum fluctuations smaller than subatomic particles and expanded them to sizes larger than today's solar systems. The process worked like photographing a microscopic pattern and enlarging it to billboard proportions. Quantum vacuum fluctuations that began at scales where the uncertainty principle dominated became classical density variations spread across cosmic distances. The Planck satellite mapped these primordial quantum fingerprints with unprecedented precision. Its measurements revealed statistical patterns in the cosmic microwave background that match exactly what inflation theory predicts for quantum vacuum fluctuations stretched to cosmic scales. The data shows how quantum uncertainty in the early universe translated into the large-scale structure we observe today. This connection between quantum mechanics and cosmic architecture becomes profound when we consider what these fluctuations actually created. Every galaxy cluster, every individual galaxy, every star system began as a quantum vacuum fluctuation smaller than an atom. The Milky Way galaxy, containing hundreds of billions of stars spread across 100,000 light-years, originated from quantum nothingness that could have fit inside a space trillions of times smaller than a single atom. The European Space Agency's Euclid telescope continues mapping how these quantum seeds evolved into today's cosmic web. Its observations reveal how matter flows along invisible scaffolding created by dark matter, following patterns that preserve the statistical signature of primordial quantum fluctuations. The distribution of galaxies across billions of light-years still reflects the quantum mechanical properties of the vacuum that existed in the universe's first moments. Modern supercomputers create detailed simulations showing how quantum vacuum fluctuations evolved into today's cosmic structures. These models start with the statistical properties of quantum fluctuations and follow their gravitational evolution across billions of years. The simulations successfully reproduce the observed distribution of galaxies, confirming that quantum mechanics operating in the early universe explains the large-scale structure we see today. The James Webb Space Telescope has revolutionized our understanding of how these quantum seeds developed into the first galaxies. Its infrared observations peer back to when the universe was only a few 100 million years old, revealing how matter first collapsed into gravitationally bound structures. These early galaxies show exactly the clustering patterns expected from quantum vacuum fluctuations amplified by inflation. X-ray observations from satellites like the Chandra X-ray Observatory map the hot gas between galaxies, revealing the cosmic web's intricate structure. This gas traces the same patterns predicted by quantum fluctuation models, providing independent confirmation that cosmic architecture originated from vacuum quantum effects. The largest structures in the universe preserve the statistical fingerprints of quantum mechanics. The realization that quantum vacuum fluctuations created cosmic structure represents one of the most profound connections in physics. It links the smallest scales governed by quantum uncertainty to the largest scales shaped by gravitational attraction. Virtual particles appearing and vanishing in laboratory vacuum chambers follow the same quantum principles that determined where galaxies would form billions of years later. This cosmic quantum connection means that the empty space around us contains the creative blueprint for everything that exists. The quantum vacuum doesn't just fill the gaps between matter, It provided the template that organized matter into the complex structures we observe throughout the universe. Quantum mechanics has revealed itself as the architect of cosmic order, transforming microscopic uncertainty into macroscopic reality. The implications extend beyond cosmic structure formation into the very fabric of spacetime itself. Gravitational wave observations provide another window into these cosmic quantum effects. The Laser Interferometer Gravitational Wave Observatory detects ripples in spacetime created by colliding black holes and neutron stars, probing the quantum nature of spacetime where classical physics breaks down and quantum effects become important. Future gravitational wave detectors planned for space will observe even more subtle effects related to quantum vacuum properties. The Laser Interferometer Space Antenna, scheduled for launch in the 2030s, will detect gravitational waves from the early universe itself. These observations could reveal gravitational signatures of inflation and provide direct evidence for how quantum fluctuations were amplified to cosmic scales. Yet perhaps the most intriguing aspect of quantum vacuum research lies not in understanding the past, but in harnessing its properties for the future. The same quantum fluctuations that seeded galaxy formation continue to permeate every cubic centimeter of space around us, carrying energy densities that dwarf anything humans have ever attempted to harness. The ultimate energy crisis solution. Scientists have begun exploring whether this quantum activity could solve humanity's energy challenges. The idea of extracting limitless energy from empty space sounds like science fiction, but quantum physics suggests it might be possible. In 1948, Dutch physicist Hendrik Casimir predicted something remarkable. He calculated that two metal plates placed close together in a vacuum would experience an attractive force, even though no energy source existed between them. This force comes from quantum vacuum fluctuations themselves. The Casimir effect works because the plates restrict which quantum fluctuations can exist in the space between them. Only certain wavelengths fit in the narrow gap, while all wavelengths can exist in the open space around the plates. This creates an imbalance in radiation pressure from virtual particles, pushing the plates together. The effect becomes measurable at micron separations, confirming vacuum energy's physical reality. Modern micro and nanofabrication labs routinely measure Casimir forces, providing contemporary context for what was once purely theoretical prediction. Scientists have spent decades trying to harness this vacuum energy for practical use. The challenge is enormous because the Casimir force becomes significant only when surfaces are separated by distances smaller than the wavelength of light. At these scales, extracting useful amounts of energy requires precision engineering at the atomic level. Yet recent breakthroughs suggest we may be approaching solutions to these technical hurdles. The International Space Federation reported preliminary successes in 2025 using Casimir-based extraction rigs aboard orbital test platforms. These systems use microstructured vacuum chambers designed to enhance energy density between nano-engineered surfaces. The goal is harvesting stable microcurrents over prolonged periods. While current energy levels remain small, the potential scalability of these systems continues under evaluation. Space-based systems may prove ideal testbeds for zero-point energy technologies due to the lack of atmospheric interference. Chris Magenti's white paper in 2025 laid out a compelling case for fractal-based nanostructures as ideal mediums to stabilize vacuum fluctuations. Fractals, due to their self-similarity across scales, naturally resonate with wideband Casimir frequencies. Magenti proposes building energy cavities that amplify subtle quantum vibrations by shaping them into recursive, high-Q fractal forms. Such structures could allow controlled modulation of vacuum energy densities, theoretically optimizing extraction rates and storage capacities. Research labs in Germany and South Korea have begun experimental designs using atomic layer deposition techniques. The computational tools for studying vacuum energy have advanced dramatically. Researchers in the UK and Portugal, led by Lily Zhang at the University of Oxford, unveiled a computational paradigm that can accurately simulate interactions between powerful laser beams and quantum fluctuations in a vacuum. This research could vastly reduce computing resources required to develop robust three-dimensional simulations of laser vacuum interactions, making them far more efficient and accessible. Ongoing experiments aim to observe light scattering and vacuum birefringence, phenomena recently studied computationally by Oxford researchers. These investigations probe how intense electromagnetic fields can polarize the quantum vacuum itself, potentially creating measurable effects from what appears to be empty space. The theoretical framework suggests that sufficiently powerful lasers could make virtual particles temporarily real, opening new pathways for understanding and manipulating vacuum properties. Quantum computing represents the most immediate practical application of vacuum energy effects. Quantum computers already harness vacuum fluctuations to perform calculations impossible with classical systems. The quantum sensors that control these systems achieve precision levels where vacuum noise becomes a fundamental limiting factor. Future quantum computers may directly incorporate vacuum energy effects into their operational principles. The Rice University team reported the first direct observation of a superradiant phase transition, where quantum particles begin to fluctuate in coordinated, collective ways without external triggers, forming new states of matter. This discovery opens possibilities for quantum technologies, including ultrasensitive sensors and high-fidelity quantum computing. These developments suggest that controlling vacuum fluctuations may become central to next-generation quantum technologies. Space propulsion represents another tantalizing application. If vacuum energy could be extracted efficiently, spacecraft could theoretically operate without carrying fuel. The energy density of quantum vacuum fluctuations far exceeds chemical or nuclear fuel, potentially enabling rapid interstellar travel. However, the engineering challenges remain formidable, requiring materials and techniques that push beyond current technological capabilities. The fundamental limitations of vacuum energy extraction stem from thermodynamic principles. While vacuum contains enormous energy density, extracting this energy without violating conservation laws poses significant challenges. The vacuum exists in its lowest possible energy state, making energy extraction theoretically difficult. Some proposals suggest that energy extraction might be possible by manipulating vacuum structure rather than extracting energy directly. Current research focuses on applications that use vacuum effects rather than extract vacuum energy. Ultrasensitive gravitational wave detectors account for quantum vacuum noise in their measurements. Atomic clocks achieve precision, where vacuum fluctuations represent measurable uncertainty sources. These applications harness vacuum properties without requiring direct energy extraction. The theoretical energy content of quantum vacuum staggers comprehension. Calculations suggest that each cubic centimeter of empty space contains more energy than all matter in the observable universe. This energy remains locked away by quantum mechanical principles, accessible only through indirect effects and carefully controlled conditions. The pursuit of vacuum energy extraction continues driving advances in quantum technology, precision measurement, and theoretical physics. Whether practical energy extraction becomes possible remains uncertain, but the research pushes our understanding of quantum mechanics and opens new possibilities for manipulating reality at its most fundamental level. Yet beyond these practical applications lies an even more profound mystery about the nature of existence itself. The final secret of existence. The deepest question humans have ever faced isn't about the stars or the galaxies or the particles that make up matter. It's simpler and more terrifying. Why does anything exist at all? This question has haunted philosophers for centuries, But 2025's quantum research suggests an answer that would shock ancient thinkers. The evidence points to a conclusion that seems impossible, yet appears inescapable. Nothingness itself may be unstable, constantly creating something from its own emptiness. Think about the logical alternative. Perfect nothingness should contain no energy, no particles, no fields, no quantum fluctuations. It should be absolutely still and completely empty. But quantum mechanics reveals that such a state violates the uncertainty principle. The vacuum cannot maintain exactly zero energy for any measurable time period. This means that true nothingness, the kind that philosophers imagined, cannot exist in our universe. Quantum field theory reframes vacuum as an active medium, where virtual particles constantly appear and vanish. This instability of nothingness may explain the most fundamental mystery in science. The Big Bang appears to have created our entire universe from a state containing no matter, no energy, no space, and no time. Classical physics cannot explain how something emerges from absolutely nothing. But if nothingness itself is unstable, if it naturally tends to create something rather than maintaining perfect emptiness, then the universe's appearance becomes less mysterious. The Big Bang may represent nothingness collapsing into existence, because maintaining perfect emptiness was impossible. The matter that surrounds us today tells a story of cosmic destruction on the largest scale imaginable. Current theories suggest that the Big Bang produced equal amounts of matter and antimatter. These opposite forms of matter should have annihilated each other completely, leaving behind only energy and returning the universe to a state resembling its original nothingness. Yet here we are, made of matter that somehow survived this cosmic catastrophe. The survival of matter required a tiny asymmetry in the early universe. For every billion antimatter particles, there were 1 billion and 1 matter particles. This minuscule imbalance determined the fate of everything we see today. When matter and antimatter annihilated each other, the leftover matter became the raw material for galaxies, stars, planets, and eventually life itself. We exist as the debris from the universe's greatest destruction event, the survivors of an annihilation so complete it left only 1 particle in a billion. Modern high-power lasers now simulate vacuum phenomena that were once purely theoretical. Purdue University's 2025 studies demonstrate how intense electromagnetic fields can create electron-positron pairs directly from vacuum fluctuations. These experiments push laser intensities to levels where the quantum vacuum itself becomes polarized, allowing researchers to observe pair creation in real time. The Opera collaboration has achieved similar breakthroughs using focused laser pulses to extract virtual particles from apparent emptiness. These laser-based experiments reveal vacuum's creative potential operating under controlled laboratory conditions. When laser intensities exceed critical thresholds, the electromagnetic field becomes strong enough to promote virtual particles into real, observable matter. The process mirrors what may have occurred during the universe's earliest moments, when extreme energy densities allowed quantum fluctuations to become the seeds of cosmic structure. Quantum sensors provide another pathway for detecting vacuum fluctuations directly. Superconducting circuits cooled to near absolute zero can measure individual photons appearing from vacuum noise. These devices achieve sensitivity levels where quantum vacuum activity becomes the dominant source of measurement uncertainty. Atomic interferometers detect gravitational effects so subtle that vacuum fluctuations create measurable interference patterns. The Large Hadron Collider's newest upgrades allow scientists to create conditions similar to those that existed microseconds after the Big Bang. These experiments produce showers of matter and antimatter particles, then measure their properties with unprecedented precision. Each measurement brings researchers closer to understanding why the universe chose matter over perfect annihilation. The answer may lie in subtle violations of symmetry laws that operate only under the extreme conditions present in the early universe. quantum vacuum fluctuations emerge as potential drivers of the universe's continued evolution. These same fluctuations that make perfect emptiness impossible may also power the universe's accelerating expansion. Dark energy, the mysterious force pushing galaxies apart at ever-increasing speeds, might originate from the quantum properties of empty space itself. If vacuum fluctuations drive cosmic expansion, then nothingness isn't just unstable, it's actively creative. The possibility that our universe represents just one quantum fluctuation among infinite others challenges every assumption about reality. If nothingness naturally creates something, then our Big Bang may be one event in an endless series of universe-creating fluctuations. Each fluctuation could produce a different universe with different physical laws, different particles, and different possibilities for complexity and life. Evidence for this multiverse theory connects directly to vacuum physics. The cosmic microwave background radiation shows statistical patterns that match theoretical predictions for quantum fluctuations in the early universe. These patterns suggest that our universe emerged from quantum uncertainty operating at the largest possible scales. If quantum fluctuations created our universe, similar fluctuations might create countless others. Modern quantum field experiments provide glimpses of this creative potential. Virtual particles appear from vacuum fluctuations billions of times per second in every cubic centimeter of space. These particles exist for impossibly brief moments before vanishing back into nothingness, but their temporary existence proves that vacuum contains unlimited creative potential. The realization that nothingness serves as the universe's most creative force transforms our understanding of existence itself. Empty space isn't passive background waiting to be filled. It's an active medium constantly generating new possibilities, new particles, and potentially new universes. What we've discovered challenges everything humans thought they knew about the nature of reality. The quantum vacuum has emerged as the central force in cosmology, technology, and fundamental physics. From the cosmic microwave background that maps the universe's earliest quantum fluctuations to the precision sensors that detect individual virtual particles, vacuum physics connects the smallest scales to the largest structures in existence. Modern experiments continue pushing the boundaries of what we can observe and manipulate in apparently empty space. Laser interferometers measure gravitational waves while accounting for quantum vacuum noise. Superconducting circuits detect single photons emerging from nothingness. Space-based quantum sensors probe vacuum properties in environments more isolated than any earthbound laboratory can achieve. Empty space isn't empty. It's the universe's engine of creation. What surprised you most about the quantum vacuum? Share your thoughts in the comments below.